Okay, we can get started now. Now that the projector's warming up. All right. God, I need to not look directly into the light. Okay. All right, so here we are. This is still week 7, right? Maybe lose track of time sometimes. Okay. So first of all, the homework is due tomorrow night, right? PA3 will be due, and so I know many of you have started already. Hopefully all of you have started already. If you haven't, then you should get started. And so we would like to have an optional help session tonight, this evening. Okay, well, the TA will be there, Jacob, and I will probably pop in as well a little bit later. But we don't know exactly where to have it because I haven't reserved a room yet. And so I don't know. And so I think maybe what we'll do is after class today, Jacob will stick around. And if you're interested in coming to this lab session, then you should stick around for a minute and you can try to kind of strategize about how to meet up. So the idea is for it to be from 5 to 7. So, you don't have to be there right at 5. That's the reason it's 2 hours long, is so that there's plenty of time for people to kind of come in. So that's why I'm not sure exactly what to do because I don't have a set place for it yet. So I'm not sure what to do. Maybe you can just hang out in ARC and find a room, an empty room in there, and like look out for people coming in. I don't know. But for next time, so the plan is to do this for future assignments as well, and hopefully then I'll have an actual room for us. Okay. Let's see. And I suppose there are some questions about the homework. So let me bring it up. PA3. Whoops. Sorry. Go. All right. I guess this is slightly different. I've modified this file and haven't committed it, but I just added some extra comments. Okay. But so first of all, I just want to point out that this initial code here is just some like library code. Okay. So there's the seek function and then all the result type stuff. So you don't necessarily have to use all this. Okay. The only thing that you're really expected to use, to be honest, is the seek function. Okay. And you only really need it for the last part of the homework, which is writing the evaluator to use the result type. Okay, so don't let this throw you off. I looked into trying, because there's a way that you can include a library. Like I uploaded this code to like Google Drive, and there's a way to like import it, but it's kind of clunky and weird, and like doesn't work on the command line version of Pirate. So I don't know. For now, I'm just going to kind of paste library code at the top of the files that I give you. Okay, it's easier this way, so just kind of ignore it.
I have a quick question. You said it'll be helpful to use the seek function on the last part of the homework.
Yeah.
What part is that?
That is the evaluator for expressions. Okay. Because what you're supposed to do here is to rewrite the evaluator from last time using the result type. Okay, so that's where that seek function will be useful. Okay, so then I don't expect you to have much trouble with the BST stuff. And then, of course, for red-black trees, the hard part is number 4. And so don't be surprised if it takes you a while to get that right. Yeah?
I was just wondering, because for the last part, I used lift 2. Is that also
That's totally fine. Yeah. So that could be useful as well. But you could just use seek to do the same thing. Lift 2 is kind of a cool trick, so you're free to do that as well. Right. Yeah. So I mean, all this stuff should be pretty straightforward, except for number 4. Might take you a while. And there are all kinds of ways to go about implementing number 4. So you can try to be creative, but don't be too creative. Okay. And then for streams, I just want to emphasize one thing about streams is that, I said this kind of in passing in previous lectures, but I don't think I really emphasized it enough, which is that when you're processing a stream, like you're writing a function, like take, for example, this lazy map function. Notice how it doesn't do cases on the stream. It just uses lazy first and lazy rest to access the first and the rest of the stream. Okay? And that's what you should always do. Okay? So lazy first and lazy rest, they do the cases inside of them. And then everywhere else, you should never do cases on a stream. Just stick to using lazy first and lazy rest. Okay? That's how we process streams. All right? So whenever you're this is not a solution file, right? Okay. Right, so when you're writing this function, don't do cases on the stream. Okay? And likewise for number 5. And there have been a bunch of questions about this function here, and students are struggling to do it. So what I would recommend is to take a look at our in-class code in the repository. There's a list.r file where we wrote a bunch of list functions, and there's one called running sum, I think, that is very similar to this. It's essentially the same problem, except we were doing it on a list instead of a stream. Okay? So I would recommend taking inspiration from that. Yeah?
Would you take points off if we did do cases inside of stream sums?
I don't know. Maybe like 1 point. Yeah. Because, well, I've told you now, you can change it.
Yeah. Okay. So we can resubmit it, right?
Yeah, you should be able to. Let me know if you can't resubmit. But yeah, I mean, so you can do it with cases, but there's a fundamental difference between streams and the other kind of data elements or data types that we've seen, where streams, you don't really want to think of them as data. A stream is not like a finite piece of data, and so when you compute with a stream, you're not like inspecting its internal structure and taking it apart. It's not a little chunk of data that you do that with, but it's more like a process that you observe the behavior of. Okay? And so it's just kind of a moral thing where you don't want to think about it as like inspecting the structure of the stream. You really just want to think of it as like observing the first element and like observing the rest of the stream. So that's how you compute with a stream. Okay. And then I can just point out one little cool thing here. So if you get to this point where you've implemented stream sums, and then you can uncomment this line and run it, and you'll see it spit out a bunch of stuff forever, like a bunch of values that are getting closer and closer to pi, but it's quite slow. And if you sit there and wait for a while, you'll notice that it gets slower and slower over time. And the reason for that is because Pyre is actually using exact nums. That the values that are being computed by our stream, this pi sequence, or the stream sums of pi sequence, well, they're all rational numbers. They're like exact rational numbers that are converging to pi. And so as you get further and further into the sequence, these rationals get like bigger and bigger. Okay, they're like arbitrary precision rationals. So the numerator is this really big number, and so is the denominator. And so that's why it gets slower and slower, because just doing basic operations on rationals starts to become slow when they get really big like that. Okay, and they can stay rationals because all the operations that we're doing preserve rationals. If the rationals are closed under under, you know, multiplication and division and addition. So all these functions, as long as you give them rationals as arguments, you get rationals as output as well. Okay. So I don't know. I just think that's cool. That you know, what we have here is a stream of rationals converging to pi. Okay, because pi, of course, is not a rational number. Right, and then I think I've said enough about the expression evaluator and the result type, I hope. Okay. So now we can get back to the slides that we started looking at. And yeah, we might, well, let's see. I don't know. I haven't had much time to prepare for today, so we'll see how it goes. Just kind of wing it, I guess. But let's review the slides a little bit. We started looking at parsers, interpreters, compilers, and just kind of the high level idea of what they are and how they differ from one another. Okay. Then we get to parsing, and the idea here is to take the concrete syntax, to take the program, the source code, okay, the program text, and to translate it, you know, read it in to some in-memory representation so that we can work with it. And we're going to call that representation the abstract syntax. Okay? And we saw some examples of that. Let me skip ahead. Okay? And then we see this idea of using a grammar. Okay? This is a BNF grammar. And I don't know if there's really a precise definition of BNF. Like, there are some variations on what that means, but it's just kind of roughly things that look like this. Okay. So here's a grammar for a little programming language, I guess, with expressions and commands. Okay. And so what these grammars are like recursive things that specify the grammatical structure of the language. And it sort of is like, it's kind of like a sub-language for expressions, and then a language of commands, and they can be recursive and they can be mutually recursive. Okay. So here we say, well, an expression is either a number or an expression plus an expression, so that's why it's recursive, or an expression times an expression. Okay, and a command could be, you know, print an expression, or an if command with an expression there, and two set commands. Okay. And you know, I mean, you know, kind of the key thing here is that these can be recursive. And I think, you know, I mentioned last time that there's one of the key people behind introducing this idea of like using formal grammars to capture the syntax of language. It was like Noam Chomsky. And a lot of what he did was, you know, he was studying natural language and introduced a way to kind of formalize the grammar of natural languages. Okay. And a really key element, though, is the recursive, that they're recursive. And, you know, I mean, a lot of this class, I keep telling you that, you know, it's all about recursion. A lot of this is about recursion. And I think a part of what I'm trying to do is to kind of convince you that recursion is not this exotic thing. It's not confusing at all. That actually, you know, everyone in this room has a very strong intuitive understanding of recursion, because it's something that you're born with. You know, when little babies are born, you know, every human child has basically an innate ability to just pick up language. You know, you don't have to teach a kid how to speak the language that they're growing up around. They just kind of pick it up. And they aren't just, you know, they aren't mimicking what they hear and parroting the words and repeating them back. They're actually learning the grammatical structure and figuring out the patterns and the rules and learning to form new sentences on their own, because they understand recursion. They understand the recursive structure of language. Okay, that we're born with an intuitive understanding of recursion. Of course, then you have to teach a kid how to read and write, and you have to kind of teach them how to formalize language with notation. And so it's essentially, for us, it's the same thing with programming, with recursion and stuff, is that, you know, you already understand recursion. You just maybe, you know, it takes some learning to figure out how to formalize it. Okay. So, you know, It's kind of, it's like you already know this stuff, you just don't know it yet, maybe. Okay, so right. There's some terminology about grammars, right? So these things that can appear on the left-hand side of rules, those are called non-terminals, and then things that only ever appear on the right-hand side, those are called terminals. Essentially, it means they can't be expanded. You can't expand a terminal because it doesn't appear to the left-hand side of any rule. Okay. And then there's this idea of a derivation, or a given string being derivable from a grammar. Okay? So you say that a string is derivable from a grammar if you can start with the starting symbol, the starting non-terminal symbol for the grammar, which there's always one that's specified as that, and you can, starting from that, you can unfold non-terminals to generate kind of intermediate forms to reach finally the string that you're after. Okay? So there's this idea of like deriving a string from a grammar, or you could call it generating a string from the grammar. Okay. And we saw some examples of that. But of course, these derivations they're interesting from a theoretical point of view, but they're not practically that useful for us. What's much more useful generally is a similar idea of a parse tree. Okay, so this gives you a tree-like representation of essentially of a derivation. Okay, so you could say, oh, actually, you can consider this to be evidence that a string is parsable by a grammar, or it can be generated by a grammar by giving a parse tree, where every non-leaf node corresponds to a non-terminal, and its children correspond to the right-hand side of one of the rules for that non-terminal. Okay, and then all the leaves should be terminals, and when you read them in order that you get the string. Okay. But then there are all kinds of issues with grammars that you have to deal with. They're kind of technical problems like ambiguity. Okay, because this grammar that we have here, there's nothing in this grammar by itself that tells you that multiplication should bind tighter than addition. Okay, so this grammar is ambiguous because if you've got a plus and a times next to one another, you don't know which way to parse it. The parse tree could be doing multiplication and then addition, or it could do it the other way around. And so there's more than one parse tree for that string, which means that the grammar is ambiguous. Okay, so if a given string has two distinct parse trees, the grammar is ambiguous. And here's an example of the same kind of thing here. Okay, and then so the way to solve this issue is to come up with what you want. How do you want the precedence levels to be for the operators, and what will their associativity be? But then you still need to find a way to kind of bake that stuff into the grammar, right? And that's where you'll be doing that in 4100, figuring out how to do that. But we're going to be skipping that and kind of taking an easy route. Okay, because parsing is kind of a complicated issue to get right. So we're going to sidestep all the problems, all the difficulties, by using S-expression syntax. So what does it say here? It says, we'll assume that all the ambiguity that is typically resolved by the parser has already been handled by the programmer. And what they mean is essentially we're just going to force the programmer to use syntax that's unambiguous. So it's kind of what Pirate does sometimes, where they force you to use parentheses in places where you normally wouldn't have to. So we're going to kind of do the same thing. So we're going to use the syntax that is especially convenient for parsing, and it turns out to be not too bad for programming in either. Okay, and it originates from Lisp, the programming language. So that's where S-expressions come from. They were used as a notation for writing programs for Lisp. And I think they were intended to just be like a temporary thing, to be replaced by some other syntax later on. But they turned out to have desirable properties even beyond just being easy to parse. So they kind of stuck around and became kind of a permanent thing. So even today, if you program in Lisp, it uses S expression syntax. Okay, but they're also useful as a serialization format, especially for tree-like data. Okay, so well, let's get to what they actually are. So here's a grammar for the SX type in Pirate. Pirate has in the standard library some support for S expressions, and this is what their thing looks like. There are 4 constructors, and there's one for numbers, there's one for identifiers, or usually called a symbol. Okay, it just means it's like a name, and then one for string. So the difference between these two is that strings are surrounded by quotations. Okay, so these are the 3 like atomic units, kind of the base S expressions. And then there's the recursive case, which is a list. Where you've got parentheses on the ends, then 0 or more, perhaps it should be 1 or more, S expressions separated by spaces. So, usually the setup is like an S expression is, it's either an atom or a list of S expressions. I can put like a star there to mean 0 or more. Okay, that it really is just, it's an atom where an atom can be sort of whatever you want. Okay, maybe it's like numbers and booleans and strings and symbols and just the kind of base types of whatever you want. Of course, booleans you could just have as symbols, special symbols. So that's why this setup that they use in Pirate is sufficiently general for anything that you would want, pretty much. You can have numbers or symbols or strings, and that's all we'll need. Or a list of S expressions. So this is the recursive thing. So that's why, obviously, you can use this to encode lists where all the things are atoms. It could be a list of atoms. But since these are recursive occurrences in SX, these themselves could be lists. So you could have a list of lists, or one could be a list and the next one could be an atom. Okay, so you can end up kind of encoding tree-like data structures as well. So it works well for syntax of a language that generally has kind of a tree-like structure.
When we use double colon equal, is that a different type of equality from single colon equal?
Yeah, I mean, this is just the BNF grammar thing. This is kind of like the meta syntax for grammars, where you say, when you have a non-terminal, and then you put double colon equals, and then the case is separated by bars. That's just the way it is. Okay. So here are some examples of S expressions where you've got the kind of normal form that you would expect, and then the equivalent S expression form of these things. So 3 plus 5, you'd write it like this, where not only are we using parentheses, but we also use prefix notation. And that makes it easier to parse. Okay? And we'll see why when we get to it. But so this is how you do it. If you want 3 plus 4 minus 5, you would say, well, plus 3, then minus 4, 5. Just prefix notation. Nothing crazy going on. And then for if B, then 3 else 4, you could write just like this, where this doesn't have to say con. It could be any keyword you want. This could say if or something, but it's common to use con. And then the Boolean expression, and then the 2 case expressions, the 2 branches. Okay. Right. So operators always prefix their arguments. Okay. Everything's prefixed, and you use parentheses everywhere. So there's no ambiguity. Okay. So now we can kind of rewrite this grammar here. Say instead of it being like this, we'll say an expression is either a number again, or here's the addition now. Now we have parentheses there, and the plus goes before the sub-expressions. And then you do the same thing for multiplication. And for commands now, you just put parentheses around these two things. And so here, now we're using ITE instead of con. We just have to pick one and go with it, so I'm not sure why they're different here. But we'll stick with one for our assignments. Okay. Okay, so now we're getting to abstract syntax. So I think we stopped right around here last time. So let's take a look at abstract syntax. All right. So abstract syntax is in-memory representation of the program stored in some kind of data structure that is easy to work with, you know, for the machine. So the question is, which representation should we use? What kind of data structure should it be? Okay. And the solution is to use a tree. Okay. Not necessarily a binary tree. Generally, it's not going to be a binary tree. But you'll use some kind of tree-like data structure where you have, roughly speaking here, one kind of node for each non-terminal in the language, and one kind of leaf for each terminal. Okay? And there's some nuance here, which we'll leave out for now, I think. But there's kind of one issue here where when you get to the tricks for like resolving ambiguity, sometimes you end up introducing new non-terminals and stuff. And basically, the grammar that you're actually using for the concrete syntax has a bunch of noise in it that you don't want to be in the abstract syntax. So then it's not really quite right to say that you have one kind of abstract syntax node for each non-terminal. But really, I mean, that would be the case here, but it's not the case in general. But really, you want the abstract syntax to be as abstract as possible, leaving out any of that kind of noisy details from the concrete syntax. And so, you know, we'll have a node for addition, we'll have a node for multiplication, okay, in the abstract syntax. So let's take a look. It says to convert the following string to an abstract syntax tree. So, okay, we've got a new thing in our grammar here, which is for sequencing of commands. Okay, so now a command can also be a command followed by another command with a semicolon in between. So we're given this string in the language. Which, when I say it's in the language, we mean it's derivable by the grammar, or it can be generated from the grammar. Okay, and so what would the abstract syntax tree for this program look like? Well, is the solution here, or do we have to do it? Okay. Well, I mean, it's fairly straightforward, I think. At the root will be the sequence. So maybe I can't draw on the screen here, but it'll be something like the colon at the root, semicolon, I mean. And then on the left, we'll have print nat 3. So I don't know how I would want to write this using notation, but print nat, and then 3, and this is a print string. Or was it hello? Okay. So I mean, it looks like a parse tree, but I want to be careful about. I want to make this distinction that a parse tree and an abstract syntax tree are not necessarily the same, because the parse tree is going to have all the noisy details from the grammar if they're there, and the abstract syntax tree will be, you know, all that stuff will be boiled away. But our grammars are sufficiently simple here that the parse tree and the abstract syntax tree are pretty much the same thing. Okay. So then how can we represent abstract syntax trees in Pirate? Here's a grammar for expressions that we've seen. And the solution is to use algebraic data types. Okay, I mean it's probably pretty obvious because it looks like an algebraic data type already. Okay, so here's a data type, and plus we've already seen something very much like this in our homework. Okay, so we can just pretty straightforwardly translate from this grammar to abstract syntax. Okay, but notice that the abstract syntax doesn't really care, like it doesn't include the parentheses because it doesn't need to. Okay, but you have a constructor for each of the rules, and we have one for numbers and it holds a number. We have one for plus that has the two sub-expressions, and we have one for times that has the two sub-expressions. Okay? And so given a string like this, that's in the language of this grammar, we could represent it in abstract syntax using this data type. Okay? And so that's kind of what we're going to do, is that we're going to have programs that are written in this kind of syntax, and we're going to be parsing them in to some data types for the abstract syntax. Okay, and then we can actually evaluate them, we can run the programs, we can type check them, we can do optimization. This is a convenient kind of representation for optimizing, and translating to other representations, etc. Okay. Yeah, the X data type encodes a set of expression trees. Okay, that it's the set of all trees that could be represented using this type. Okay. Well, here's another in-class exercise. So here we're given an expression here. We're given some abstract syntax. Okay, so you can see already, well, we mentioned last time that it's not very convenient to program in abstract syntax. This is what it looks like. It'd be really annoying if you had to write everything like this when you were programming. But what is this? We have times on the outside, and then on the left sub-expression it's 3 plus 4, and on the right sub-expression it's 5 plus 6. So what's the tree? You got times, and what was it? 3 plus 4, so plus 3 and 4 times 5 and 6, something like that. Okay, so it's totally unambiguous now because essentially the associativity or the parenthesization is just built into the structure of the tree. Right? So we don't have to worry about that anymore. Okay. Here, we're actually writing out the constructor names. Probably better to do it that way. Okay, now we need to write down the expression corresponding to this tree. What would it be? Well, on the outside, it's an E plus. So I'll do that. E plus. And on the left, it's an E times. The left child. E times. And it was 1 times 2. So for each of those is an enum, I think it was called. Enum, wait, what was it? 1 and 2. 1. Enum 2. That's our times. And then the right child of the plus was just a 3. E plus, whoops, 3. Whoops, yeah, you're right. There we go. E's a little bad. Okay. Yeah. So it's fairly straightforward. Okay, but we'll get to, when we get to our language in the next, starting in the next homework assignment, our language will be a little more interesting than this. Okay, that we'll have a bit more than just plus and times. Okay, and then we'll extend our language in the next assignment to include even more things. Okay, so now I suppose we could look at Pirate's support for S expressions, because we're going to be using S expressions. And Pirate's S expression stuff. So let's see. Oops. Here we go. I think there are two libraries. There's one called SX and one called SX structs. Okay, so what do we have here? Well, let's go to structs first. This has the actual data type. Okay, so here's the data type for SX. And they say it defines the result of parsing S expressions. Okay, so Pirate provides for us a parser for S expressions. Okay, so we'll look at that next, that read SX thing. But here's the data type, and it's essentially what we've seen already. There are 4 constructors. Okay, 3 of them are for the atoms, the different kinds of atoms. There are numbers, strings, and symbols. Okay, and again, strings. This is what you'll get from parsing in a string that has quotations around it. But symbol is what you'll get from strings without quotations. Okay, and then it could also be an S list of a list of S expressions inside. Okay, so there could be 0 or more S expressions there. All right, and I think that's pretty much, there's some helper functions here. But that's the data type. So now let's go to the other library, the other module. Okay. And here we are, read SX. This is kind of weird. They don't give the return type, but they give the argument type. So read SX, you give it a string. And what it returns is an SX value, okay, for that string. So let's see, it satisfies this grammar, yeah. And they give some examples. Okay, and so what happens though is that when you call read SX, when you give it a string, what are they doing here? Okay, they're saying let P be s.read_sx. So P is the function that parses a string as an S expression. And then they got some tests where they're using P on some strings, and some of them work. Actually, all of these work. Okay, but what happens though is that if the input string is not a valid S expression, like right here, there's an unbalanced number of parentheses, it'll raise an error. So, and it's using the kind of nasty error stuff that we don't like very much. They're not using a result type or the option type, so we're just going to have to live with that fact. Okay. So our strategy for parsing in this course is going to be, take the string and first parse it as an S expression using this. And if it fails, then okay, it'll just raise an error. But if it succeeds, we get an SX, and then we have our part of the parser, kind of phase 2, that will translate the S expression value to a value of our abstract syntax. Okay, so it's kind of like, let me insert a page. So you can think of it like, imagine here's the set of all strings. Okay, all strings. Okay, so now there's some subset of the set of all strings that is like the set of syntactically valid S expressions, right? So that means, if you take a string from the set of all strings and pass it to the S expression parser, well, if it's out here, then you'll get an error, and if it's in here, it'll succeed, right? So if it's a valid S expression, then not only does you can think of the parser as like a decision procedure for just telling you, is the input string a valid S expression or not? If it's not, it'll throw an error, and if it is, it doesn't just say yes. It actually gives you evidence of the fact that it is a valid S expression by giving you the parse tree. That's like a proof. Okay. But then there's a second phase to this. There's a even further refinement, or a smaller subset. There's even a subset of all the syntactically valid S expressions are going to be the valid, scheme 0. That's going to be the name of our language. Okay, so There's an even smaller subset of strings that are valid Scheme 0 programs. Okay, and so then our part that we implement is going to be this kind of second phase where you give it an S expression and it'll kind of tell you no if it's not a valid scheme program, or if it is, then it'll give you the abstract syntax of the scheme program. Okay, and so there's just kind of like, you know, the parser is kind of like a filtering mechanism in a way, and if it succeeds, then you can keep going with your program. Okay, and we're out of slides. We've got a couple minutes. We don't really have enough time to like do much coding because I kind of wanted to go through an example of doing this, not for Scheme 0, but for like a smaller example. Because what we could do is write like a recursive descent parser to do this, but we'll probably have to do that on Monday. Yeah. So let me think if there's anything else I want to say that I have time for. Not sure. So we might just end it here. We'll see if we have a quiz. You have a question?
Yeah, when you were talking about atomics, are atomics and terminals the same thing, or is there a difference?
Well, yeah, like the atoms I was saying.
Yeah.
Yeah, those are the terminals of,
Okay,
of,
the same thing.
of the S expression
Okay.
grammar. Yeah.
Okay.
Yep. Well, okay, let's see if we have a quiz. I have to think of a question. Yeah.
So I was wondering, so is like for like type enforcement and everything, is that actually happening with the schema stuff, or is that like, is there like how, I don't know, is there any like type of like design for S expression that makes like that enforces types, or is that?
Okay, that's a good question. So the types are not encoded in the grammar. So actually, in this picture, there's going to be an even smaller subset, if I can find it. This is going to be the set of well-typed Scheme 0 programs, where there's a second phase where we do the type checker. And so what we'll see is that there actually are there will be some programs that are syntactically well-formed, so they're derivable by the grammar, but are not well-typed. And so, yeah, we're not building in the types into the grammar. It is, when you get into some really fancy type theory stuff, with like indexed data type, you can use like these things called GADTs and like Haskell and stuff. You can do that. There are ways of actually encoding the types, the type system into the syntax, but that's we're not doing that here. That's a good question though. Okay. Let's see. Okay. Well, so if you're interested in the lab, then stick around and speak with Jacob. Try to figure out what to do.